All right, it's 4 o'clock. Let's go and get started. So first of all, let me thank everyone. Thank you guys for being flexible today. It was kind of a last minute thing. I started smelling gas in my house over the weekend, and we found out there's a leak in the dryer, and so we had to fix it today. It was either today or sometime next week, and so I just thought I'll just work from home, get it fixed, and then I can wash my clothes because I am almost out of underwear, and so it would be good for me to get it fixed so I can come to campus with fresh underwear, which is always a good thing. Okay. All right, so just today we're gonna be virtual, and then Thursday I'll be back in class. So the repairman came earlier, he fixed it, it's all good. So we good to go. So I'll be back on Thursday. All right, so good afternoon, everyone. How's everyone doing today?
All right, just a bit wet.
Just
cozy.
Yeah. It's cold today. Yeah, it's very rainy. It's very cold on voting day. Of course, it just happened to be like that. By the way, if you're registered to vote, you better fucking vote. So I'm not that much older than you guys, and I'm sick and tired of people always blaming young people for not voting and having all this bad stuff happen in the country. So vote. I don't care what you vote for or who you vote for, just fucking go vote, okay? If you're registered, you got one in the mail, just mail it back. It's like no big deal. So just make sure you do that. I walked out in the rain to my mailbox today to make sure I voted. So you guys have no excuse, right? Okay. So in terms of our plan for today, we're going to continue where we left off on Tuesday, and so we are we're going to be talking about inverse dynamics analysis. So I think I left off right before I was going to do an example. So I have 2 examples planned for today, and so and they're both kind of the same. I think inverse dynamics is generally a little bit better than inverse kinematics, which is what we finished. Kinematics is definitely, I think, probably the hardest part of this section. Dynamics is kind of just applying what you've already known about free body diagrams and all that stuff. And so it is a little bit math intensive, but I think it's a little bit easier to comprehend. Right? Okay. Another announcement I want to make is that all the groups have been formed for the final project, and so you should have gotten an email from me either confirming your group. I think I may have added a couple. I may have added a person or 2 to your group, but all the groups are formed, and so we do have one more group that I thought we would have. So we do have 11 groups, but that's okay. 11 is fine. 12 or 13 is not fine. So I think what I'll do is I'll have the final presentation just be a little bit shorter than what I originally planned. Originally, I had planned for the final presentations to be about 15 minutes long, but now that we have 11 groups, I think I'll make them probably closer to 12, 13 minutes. And so 11 groups is fine. And so your groups, the group sizes range from either 3 people to 5 people. So I think that's perfectly fine. So you guys can definitely go ahead and start working on the project. All the groups are finalized. And everyone's working on a different topic, which is great. Okay. All right. Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. And this section was about inverse dynamics. Okay. And just like any kind of dynamics analysis, what we're interested in is computing the forces and torques and moments that are needed to generate motion. Okay. Okay, and so that's generally what dynamics hopes to achieve. And so once you've basically are done describing the motion with kinematics, the next step is to compute the forces and moments that are needed to actually produce that motion. And we're going to be doing the same thing here, just with the human body. Okay, and so specifically when we talk about inverse dynamics or dynamics of the human body, what we're mostly are concerned with is computing the forces and moments at the joints. Okay, And so very similar to what we did for the static analysis in this class, it's just now we're going to do it with dynamics, okay? And so the biggest difference that you'll see is that, instead of setting the sum of the forces equal to 0, the sum of the moments equal to 0, we're going to set them equal to, the equations of motion. And so we're going to have mass times acceleration and moment of inertia times the angular acceleration, okay? And so I think this is what we ended with last time. And so basically, for a 2D case, we're going to have the sum of the forces in the x direction. This is going to be equal to the mass times the acceleration in the x direction, okay? Then we have the sum of the forces in the y direction. This is equal to the mass times the acceleration in the y direction, okay? Okay, then of course we're going to sum the moments around the segment. And so when you sum all the moments in the segment, that's going to be equal to the moment of inertia of the segment multiplied by its angular acceleration, okay? Plus this extra term, it's a cross product term. So it's R times MA, okay? And that extra term there has to do with the fact that, if you sum the moments around a location that's not the center of mass, you have to add some additional centripetal force terms, okay? Okay. All right. And so before, before when we did our statics analysis, all this would equal to 0, and we didn't have to worry about this. And so it didn't really matter where we summed our moments around because we just picked a location that was convenient. But in dynamics, because we have this extra term here, it's actually going to be beneficial for us to choose. It's actually going to be really beneficial for us to choose a certain location. Okay, in particular, because we don't want to include this extra term, because this extra term here, this cross product term, can be kind of a pain in the butt to compute. So generally, we're gonna sum our moments around the center of mass, so we just don't have to worry about that at all. Okay, and so if we don't do this, and so this cancels if we choose center of mass. Okay. And so if we choose the center of mass to sum our moments around, then that's going to cancel. And so the sum of moments is just going to be equal to I times alpha. Okay. And what we're going to be able to do is that all of these terms right here, okay, the acceleration in the x direction, the acceleration in the y direction, and the angular acceleration, these are determined by our kinematics analysis. Okay. And so generally speaking, the analysis that we're about to conduct, this is done after a motion capture study. So after you've done motion capture, or maybe some other kind of kinematics analysis, you already know what the acceleration of each of the body segments are, both its linear acceleration as well as its angular acceleration, okay? You know the mass, of course, and you can compute the moment of inertia pretty easily. And so generally speaking, you'll know everything that's on the right side of these equations. What you're going to be solving for is going to be on the left. Okay. Okay. And so generally speaking, the unknowns in our equations are going to be forces. They're going to be unknown forces, unknown moments, and they're going to appear on that side. And so after we form the equations of motion, we're going to manipulate the equations so that we get our unknowns on one side and everything known on the other. Okay, and so that's generally our approach, and so that's all there really is to it. And so in a sense, it's very similar to what we did how we did static analysis. We formed our equations of motion, we set it equal to what they need to be, and then we manipulate those equations in order to get, you know, the quantities that we need. Okay. And so that's very similar to what we've done. And so we should all be very familiar with that in this class. It's just that now that we're in dynamics and there's you know, all these kinematics that we have to deal with, the math and the algebra for it gets a little bit more intense. But I just want to let you know that, you know, what we're looking for is essentially the same thing, or, you know, the process is still the same. It's just that there's just a bit more math involved in it. Okay. And so I want to talk about this first, just because, you know, once we start the example, you'll see that the math will get pretty detailed and pretty intense. And I don't want you to kind of lose sight of what we are really looking for, you know, among all those weeds. And so this is kind of the goal of what we're searching for. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's do an inverse dynamics analysis of a squat. Okay. All right. And so, you know, this is not going to look like a person. And so it's going to be, I'm going to use basically sticks for all the limbs. But we're going to start down here. We're going to have the foot. Okay. And so we're going to assume that the foot is planted on the ground. And so the foot itself is going to stay stationary, but all the other limbs like the shank and the thigh are going to be moving. Okay. All right. And so of course, attached to the foot is our ankle joint. Okay. Attached to the ankle joint, we have our shank. Right. So remember, our shank is our lower leg. The shank is connected to the knee joint. Okay. And the knee joint connects the shank to the next leg segment, which is the thigh. Okay. And then attached to the thigh is the hip joint. Okay. And then attached to the hip joint, you know, we're basically gonna lump together the entire upper body. So this is the upper torso, the upper extremity, the spine, and the head. Okay. And so, you know, for a squat, you know, what we're mostly concerned with is the legs. And so we're going to focus most of the detail there, and everything else we're just going to lump together in one. Okay. Right. So this entire segment up here, this is like the upper body. Okay. All right. So it's a little bit out of scale. So the shank is really long, and the thigh is kind of not very long. And so, you know, but just kind of use your imagination. All right, so in addition to that, we also have the properties of each of the different segments. Okay. And so for the shank, we know the mass of the shank and as well as its moment of inertia. So I'm going to call it I1, M1, I1. Okay. We know the total length of the shank. And so the total length of the shank is L1. And we also know the location of the center of mass. And so we'll call that R1. Okay, so the R1 is the distance from the ankle joint up into the center of mass of the shank. Okay. All right, next we have the corresponding properties of the thigh. And so we have the mass of the thigh, M2, and then the moment of inertia of the thigh, I2. Okay. The distance from the knee joint to the thigh center of mass is going to be R2. And then the total length of the thigh segment is going to be given by L2. Okay. Okay. And then we also know the mass, the total mass of the upper body, as well as its moment of inertia. We'll call that M3 and I3. Okay. and that's going to act at a distance of R3 away from the hip joint. Okay, so there's quite a few stuff going on, and so make sure you get all the details in the figure because it is a lot. Okay. In addition to that, we're going to assume we know the kinematics, and so we know all the joint angles. So theta 1, theta 2, and theta 3, those are all the joint angles for our lower body segment here. Okay. Okay. And so everything that I've labeled in the figure, we're going to assume that we know those. Okay. Okay. So everything there is known. And so based on all the known quantities here, what we're interested in computing are the net forces and net moments at the ankle joint, the knee joint, and the hip joint. Okay. All right. So there's our problem. And if it wasn't clear from the figure too, we're basically viewing someone doing a squat from the side. And so if you imagine someone squatting down, then we're viewing them kind of as a side profile. So that's why the bends are kind of as you see it, in the figure. Okay. Okay. All right. So before we start, it's always good to kind of quantify or to list out how many unknowns that we're going to have at each joint. Okay. And so generally speaking, for most joints, you're going to have 3 unknowns. So you're going to have 2 force components. And so generally you're going to have a force in the X direction, a force in the Y direction, as well as an unknown torque or an unknown moment. Okay. Okay. And so if we are trying to compute the net forces and moments at 3 different joints, that means we're going to have 9 total unknowns. So 3 unknowns per joint multiplied by 3 joints. And so that's 9 unknowns in total. Okay. Okay. And so if we have 9 unknowns, that means we're going to need to generate 9 different equations. Okay. All right, so it is a doozy. So it's a lot. It's definitely a lot to compute. And so it's good to kind of be organized and kind of lay out kind of what we need to do before that. Okay. All right. So before we start doing free body diagrams and stuff, are there any questions on just the setup for this example? T here, joint. Okay. All right, so let's go ahead and get started. So, so generally speaking, when you start to form these equations, the best rule to go by is to go from the most external segment and then work your way inwards. Okay. Okay. The reason for this is that generally, the most external segments, those are going to be the ones that are interacting with the outside world. And so you're going to have some measure of external forces that are measured on those external segments. Okay. Okay. And so usually you're going to need some kind of measure of an external force to start to kind of kickstart your dynamics analysis. Okay. And in fact, for this one, I did forget to label the external force. And so what we're going to assume for this squat is that this person is standing on top of a force plate. Okay. Okay. And so one thing I forgot to include was that at the foot, we're going to have an external force of Fg, where Fg is the normal force, the ground reaction force that's being applied from the ground. And we're going to assume that that's measured by a force plate. Okay. All right, so usually you're going to want to start at a location like this, but sometimes you're going to be in places where you don't have external force measurements, okay? And actually the homework problem is like this as well. And so in those cases, you're going to want to start actually in the opposite place where, you can measure kind of like the gravity force, okay? And so what you'll see in the homework problem, and if you looked at it, you'll probably know, we actually don't have a measure of the ground reaction force. And so you would actually kind of start this analysis on the other side, because what you can say is that the upper body is kind of exerting an external force on the lower body segment. Okay, but that's for the homework problem. But for now, we're going to assume that we know that ground reaction force, and so we're going to start our analysis with the foot. Okay. All right, so let's start by drawing a free body diagram for the foot. All right, and so the foot is something like this. We're going to assume that the ground reaction force is being applied at the toe. Okay. And just to be kind of general, we're going to assume that the ground reaction force has two components, a component in the y direction and the x direction. Okay. I know in the figure above I just drew it in the y direction, but we're going to assume that it's in both directions. Okay. All right, so let me go ahead and draw on the ankle joint. So this right here is the ankle joint. Okay, and then at the ankle joint, we're going to have the reaction forces at the joint. Okay. Okay, and so we're going to have a reaction force in the x direction. So that's going to be Fx1. And then we're going to have a reaction force in the y direction, Fy1. And then we're also going to have a torque or a moment at the ankle joint, and we'll call that T1. Okay. Okay. And one thing that we also know is that, we know the length of the foot. And so the distance between the toes And the ankle joint, we're going to say is a horizontal distance L. Okay. Okay. And so I'm just kind of repeating what I said. So Fx1, Fy1, and T1, these are the net forces at the ankle joint, and this is what we're going to solve for. Okay. Okay. All right, so let's go ahead and form our equations of motion. All right, so let's go ahead and sum the forces in the x direction. All right, and so in the x direction, we have two forces here. And so we have the ground reaction force in the x direction, which is Fgx. And then we have the reaction force in the x direction at the ankle joint, which is Fx1. Okay, they're going in opposite directions. And so we're going to put a minus sign on Fx1 because it's going to the left. Okay. Those are the only forces that we have in the x direction. And so we're going to set this equal to m a ax. Okay, where AAX is the acceleration of the also AFX. Let's call it that. Okay, so AFX stands for acceleration of the foot in the x direction. Okay. All right, so we're going to do the same thing in the y direction. And so in the y direction, we have FGY minus FY1 is equal to MAFY. Okay. And then we're going to have the sum of the moments. And so their foot, we're assuming the mass of the foot is negligible. We're not given any mass there. And so we can actually sum up the moments around anywhere here. And so we're going to sum up the moments around the ankle. Okay. And so if we sum up the moments around the ankle, we get FGX. I forgot something here. We also know the height of the foot. So the height of the foot is H. Okay. And so we have FGX times H minus FGY times L minus T1, because T1 is given in the clockwise direction. Okay. This is equal to the moment of inertia times alpha. Okay. So there's one thing I forgot, when drawing the figure, and that's the height of the foot. So make sure, you kind of revise your figure to include that H, which is just the height of the foot. Okay. All right. So these are our three equations. We can actually solve this outright, which is actually not that common in these kinds of problems, because each of these are only going to have a single unknown. Okay. Let's remember what we said. So our unknown quantities in this problem are Fx1, Fy1, and T1. Okay. And everything else here we theoretically know. And so we know Fg, both the x and the y component, because remember those were measured by a force plate. So Fgx, Fgy, these are known. Okay. Presumably we can measure our own foot, and so we can take a ruler and measure H and L. So those are known. Okay. And all the masses and accelerations are also known as well. Okay. And in fact, we're going to make a reasonable assumption here. So when you're doing a squat, and so when you're kind of squatting down, your foot's not really doing anything. And so your foot's just kind of just staying planted on the ground. And so for this part, we're going to assume that our foot is stationary. Okay. And so if our foot is planted on the ground and it's stationary, that means its acceleration, both the linear acceleration, AFX, AFY, and alpha are also going to be equal to 0. Okay. Okay. All right, and so with those in mind, we can solve these equations for fx1, fx1, fy1, and t1. Okay, so we have fx1 is equal to fgx. Okay, fy1 is equal to fgy, and then t1 here is equal to fgx times h minus fgy times l. Okay. All right, and so in this particular case, we were able to solve for all 3 of the unknowns, from the equations kind of straight up, and so that's not typical. And so there are situations where you're not going to be able to do that, and so but this is kind of a special case. And so when you have only 3 unknowns, 3 equations to do it, you can solve for all the unknowns from the equations. Okay. All right. Any questions on this? Okay. All right, so we started with a fairly easy one. So even though this is a dynamics analysis, we started with a segment that was actually stationary, but now we're actually going to factor motion into this thing. Okay, and so moving up from the ankle, we're going to move to the next body segment, which is the shank or the lower leg. Okay. All right, so let's go ahead and draw a free body diagram of the shank. Okay. Okay, so here's our shank. And so on the bottom here, we have the ankle joint. And up top here, we have the knee. Okay. And so the shank is kind of right in between these 2. Okay. So first thing I'm going to draw here is I'm going to draw the center of mass. And so we'll assume the center of mass is right here. Okay. Okay, so the center of mass has a mass of m1, and we're going to assume the moment of inertia with respect to the center of mass is I1. Okay. We know the distance between the ankle joint and the center of mass is R1. And the distance of the length of the entire segment here is L1. And we also know the angle, the joint angle at the ankle joint, which is θ1. Okay. And so that's actually going to be relevant in this part of the problem. Okay. And so now let's go ahead and draw in the forces and moments at the joints. Okay. So first we have the ankle. Okay. So we have fx1, fy1, and t1. And then we're going to have the same thing at the knee, except we're going to label it differently. And so at the knee, we're going to have fy2, fx2, and then t2. Okay. So now that we're kind of moving up the body, our next set of unknowns are going to be at the knee. Okay. So t2, fy2, fx2, these are now our unknowns. Okay. Because we've already solved for fx1, fy1, and t1 in the previous step. Okay. Okay. And so once again, we're gonna form the equations of motion. We're going to use those equations of motion to compute these unknowns, and then we'll go from there. Okay. But before I do that, I want you to kind of look and see at the reaction forces at the ankle joint. Okay. And so while it's true that fx1, fy1, t1, we did solve for these in the previous part, I want you to look at the directions that we've chosen for these quantities. Okay, so fx1 is going to the right, fy1 is going up, t1 is going counterclockwise. Okay, let's compare that to the ankle reaction forces that we drew when we did our previous free body diagram on the foot. Okay, and so on the foot, fy1 is going down, fx1 is going to the left, and t1 is going clockwise. Okay, and so if you notice, the directions that we chose here for the shank are all in the opposite directions. Okay. Okay. And that's on purpose, right? And so if you remember Newton's third law, you know that any force that's being applied on an object has an equal and opposite force in the opposite direction, right? And so whatever directions that we choose, it's up to you which direction that you choose for these forces. But just know that when you draw those forces on the adjacent body segment, they have to go in the opposite direction. Okay. Okay. Because they're acting on different body segments. Okay, and so whatever force is being applied on one, the opposite direction has to be applied on the other one. Okay, and it makes sense when you think about it. If you think about what's supplying these actual forces at the joints, right? And so this force that we're applying here at the ankle joint, that's being applied onto the shank. The only place where that could come from is from the foot, right? And so because the foot is the only thing else there. And so and so these forces are essentially contact forces. And so, the force that the foot applies onto the shank is going to be equal and opposite to the force that the shank applies onto the foot. Okay, and so that's kind of where these come from. Okay. All right. Any questions on that? Does that make sense? Why we, when we have the same forces on an adjacent segment, we choose the opposite direction? Okay, good. All right, so let's go ahead and form our equations of motion again. Okay, and so just like before, we're gonna have the sum of the forces in the x direction, some of the force in the y direction, and some of the moments. Okay. Okay, so let's start with the sum of the forces in the x direction. And so in the x direction, we just have two forces here. So we have the reaction force at the ankle joint, as well as the reaction force at the knee joint. They're going in opposite directions. Fx1 is going to the right, Fx2 is going to the left. And so we have Fx1 minus Fx2. Okay. This is equal to m1, which is the mass of the shank, times ASX. Okay, so that's the acceleration of the shank in the x direction. Okay. We're going to do the same in the y direction. And so in the y direction, we have Fy1 coming from the ankle, Fy2 coming from the knee. And also a y direction force that's acting on this shank is the gravity force, because the shank, unlike the foot, we are going to consider the mass of the shank. And so we have minus m1 times g. Okay. And that's going to be multiplied by m1 times ASY, which is the acceleration of the shank in the y direction. Okay. All right. Next, we have the sum of the moments. And so, for this segment here, which actually will be in motion, and so we're going to consider its motion, it's going to matter where we choose our location where we sum the moments around. Okay. And so remember what we said at the beginning of class. And so for these situations, it's best to sum the moments around the center of mass. Okay. And so our center of mass is this kind of ball location in the middle. Okay. And so this sum of the moments is going to be around the center of mass right here. Okay. All right, so let's go ahead and tally up the moments. And so we actually have quite a few here. And so first we have the raw moments, which are just T1 and T2. Okay, so we have T1. Since that T1 is going in the counterclockwise direction, we choose it to be positive. And then we have minus T2. And so T2 is a raw moment going in the clockwise direction. So we're going to put a negative there. Okay. And then we have the moments induced by all of the reaction forces. Okay, so we're going to need to use a little bit of trigonometry here. Okay. So first we have F. Let's start with the ankle joint. Okay, so we have Fx1 multiplied by R1 sine theta. Okay. Then Fy1 R1.
Wouldn't that first FX term be negative? Because it's going. Sorry, no, my bad, yeah.
Yeah, it's counterclockwise. Yeah, it's tricky. Definitely, it's definitely good to check. So, definitely good to kind of check those things. But yeah, so when you're summing the moments, it's important to check, which direction it's going, and make sure you do it relative to the center of mass here. And so for Fx1, we're going around this way, and so Fx1 will be a counterclockwise, and so that'll be positive. And then Fy1 is going around this way. And so that will be a clockwise moment. So that will be negative. Yeah. No, it's always good to question and check for sure. So that was definitely good. Okay. And then we have the same things for the knee joint. And so we have Fx2. Okay. Here, we're not given the direct distance. And so for Fx1, Fy1, we're given the distance R1. Okay. But the distance between the knee and the center of mass, this distance, okay, this distance is given by L1 minus R1. Okay. All right, so Fx2 times L1 minus R1 multiplied by sine theta 1. Okay. And so that's positive, and then minus Fy2 L1 minus R1 cosine of theta 1. Okay. And since we sum the moments around the center of mass, the only thing that we have is just the moment of inertia times the angular acceleration of the shank. Okay, so it's I alpha 1. Okay. All right, so quite a bit more stuff. Quite a bit more stuff to do, but it's as long as you're systematic about it, as long as you kind of take everything step by step, you can get every one of these terms. Okay. All right, any questions on this so far? Okay, good. And so these are our equations, and so of course the unknowns in these equations are these. Okay, everything that's marked with a 2. Right, and so, because we have three equations here for the three unknowns, in theory, we should be able to solve it. But there's actually one other issue here that we need to address, and that is these quantities, okay? So ASX, ASY, these are the linear accelerations of the shank body segment. Okay. If you recall from our kinematics unit, we don't actually obtain linear acceleration. We don't obtain linear velocities or any of that. What we do obtain are the angular quantities. So angular, angular position, angular velocity, angular acceleration. Okay. And so this set of equations actually is incomplete because we need to come up with expressions for these quantities. Okay. Okay. And to do that, I'm actually going to utilize a technique that you'd use in homework 4 actually. And so if you remember, I think it was problem 3 on homework 4, the inverted pendulum. What I had to do was I said that if you have an inverted pendulum, we can compute the x component of the position, the x position of the pendulum using that formula. And then I had you take derivatives with respect to time in order to generate the velocity and acceleration. Okay, so we're going to do the exact same thing here. Okay, so let's do the x direction one first. Okay, and then we're going to do the same thing for the y. Okay. And so for the x direction, and we're going to measure this relative to the ankle. So our ankle here is kind of like our origin. Okay, and so relative to the ankle, the x position of the center of mass here is going to be r1 cosine theta 1. Okay. Okay, so that's the x position of the x position of the shank center of mass. And so what we're going to do from here is I'm going to start taking derivatives with respect to time. Okay, so VSX, this is going to be the velocity of the shank in the x direction. Okay, so that's going to be the derivative with respect to time of XSX. Okay, kind of a tongue twister there. Okay. And so if we take the derivative of this with respect to time, R1 is just the position of the center of mass or the length along the shank. And so that's not going to change. So R1 here is going to be the same. Okay. But the angle theta 1, that is going to change with time. And so we're going to take the derivative with respect to time of cosine theta 1. Okay. And we do this. We take the derivative of cosine, we get minus sine, and so we have minus R1 sine theta 1. Okay. And then by the chain rule, because the one that actually changes with time is the theta. It's not really the cosine. And so when we take the derivative of cosine of theta 1, we have to use the chain rule to kind of take the derivative of that theta 1 on the inside too. And so this is minus R1 theta 1 multiplied by omega 1, where omega 1 is the angular velocity of the shank. Okay. All right, so we're going to do the same thing for the acceleration. So for the acceleration, we're going to take the derivative with respect to time of minus R1 omega 1 sine theta 1. Okay. Once again, R1 does not change with time, and so we're going to factor that out. So we have a minus R1 out here. Okay. And then we have the time derivative of omega 1 times sine theta 1. Okay, so we have the product of two things that vary with time. So we have omega 1 and theta 1. Both of those are going to be vary with time. And so when you take the derivative of a product like that, you have to invoke the product rule. So derivative of the first times the second plus derivative of the second times the first. Okay. And so in this case, the derivative of the first, the derivative of omega 1 is just going to be alpha 1. Yes, we have alpha 1 sine theta 1. Okay. So that's the derivative of the first. So this right here, this is the first. Sine theta 1 here is the second. Okay. And so derivative of the first is just the angular acceleration multiplied by the second, which is sine theta 1, plus derivative of the second. And so we take the derivative of sine theta 1. The derivative of sine theta 1 is just omega 1 cosine theta 1. Okay, once again, we're using chain rule. And so derivative of the second multiplied by the first, which is omega 1. Okay, and so ASX here is thus minus R1 times alpha 1 sine theta 1 plus omega 1 squared cosine theta 1. Okay. Okay, so that's the linear acceleration of the shank in the x direction. Okay, so you're going to need to do this whenever you do these inverse dynamics problems. Is you need to kind of take this take those derivatives. Okay, let's do the same thing for the y. And so in the y direction, you have y sx is equal to r1 sine theta 1. This right here is the y position of shank center of mass. Okay, and I'm just going to go through the same thing. So I'm going to go a little bit faster here, just because I'm not going to narrate every single step, but it's going to be the same process. And so we're going to take derivatives with respect to time. We're going to use the product. We're going to use the chain rule, product rule, kind of as we need it. Okay. And so VSY is going to be R1 omega 1 cosine theta 1, and ASY is going to be R1 alpha 1 cosine theta 1 minus R1 omega 1 squared sine theta 1. Okay. Okay. All right, so make sure you kind of brush up on your chain rule and your product rule, because you're going to need it for these parts. Okay. All right, and so once we solve for ASX, ASY, we just kind of plug them in up here. Okay, so it's going to form kind of a somewhat nasty equation. I'm not going to write it all down just because I want to make sure I finish this example today. But you can look at the full expression in the notes. Okay. All right. Any questions on that? Okay. All right. So that's the shank. Okay. And so we've solved for expressions for 6 of the unknowns. Okay. By the way, the reason I'm not inputting any numbers for this one is that I really want you guys to to learn the process. And I think that that kind of gets lost a little bit once you start plugging in numbers. And so I'm doing everything in terms of symbols just so that you can kind of explicitly see everything that I'm doing. Because if you plug in numbers, it gets a bit kind of hard to kind of follow that. Okay. All right, and so finally, we're going to do the same thing except at the thigh, and that's going to allow us to solve for our last 3 unknowns, which is F, X, F, Y, and T at the hip joint. Okay, and so we have our thigh free body diagram. It's our thigh. Oh, I kind of drew the shank the other way, but that's fine. Okay. Sorry, I was just checking the figure. Okay, so our thigh, down the bottom, we have our knee joint. And up top here, we have our hip joint. Okay. Let me see what colors I use for that. So for the knee stuff, I did blue. Okay. Okay, so first we have the net forces and moments at the knee joints. We have Fx2, Fy2, and T2. Okay. Remember, they are going in the opposite direction because they are, we chose an opposite direction for the shank. Okay. And then we have the corresponding ones at the hip joint. And so at the hip joint, so we have Fy3, Fx3, and T3. Okay. All right, so the center of mass is located there. So we have M2, I2. Okay. We have the angle of rotation. And so we have the joint angle at the knee. And so that's given as theta 2. Okay. And then we also have the locations of the center of mass as well as the total length of the thigh. So we have R2, and the total length here is L2. Okay. All right, so just like we did at the shank, we're going to form our equations of motion. Okay, so we're going to sum up the forces in the x direction, sum up the force in the y direction, and sum up the moments around the center of mass. Okay. All right, so some of the force in the x direction, we have Fx2 minus Fx3. This is equal to M2 ATX, where ATX here is the acceleration of the thigh in the x direction. All right, so next we have the sum of the force in the y direction. So we have Fy2 minus Fy3 minus M2G, where M2G is the gravity force. This is equal to M2 times ATY. Okay. And then we have the sum of the moments around the center of mass. And so we have T2 minus T3 plus Fx2 R2 sine theta 2, okay, minus Fy2 R2 cosine theta 2 plus F3 times L2 minus R2 sine theta 2 minus Fy3 times L2 minus R2 times cosine theta 2, and this is equal to the moment of inertia times alpha 2. Okay. Right, so they look similar, and so there's not too much different here compared to the previous one, except everything, all the indices have been shifted up by 1. So all the 1s became 2s, all the 2s became 3s, and we have a fresh linear acceleration to compute. Okay. Okay. All right, just like last time, the last thing we need to do to complete these equations is to compute ATX and ATY. Okay. So let's go ahead and do that down here. All right, so let's start with the x position of the thigh. Okay. And so this is when things are going to get really nasty, because we need to make sure that when we compute x position and y position, that they're all relative to the same origin, right? So remember when we did kinematics, we made sure that we always kind of had the same origin, and so we always made sure that the lab frame was something that we could reference. Okay, the same thing is going to apply here, and so it's tempting to say that the xtx is just going to be r2 times cosine theta 2, okay? And so this on its own would just be the x position of the thigh relative to the knee, okay? Okay. But the knee is not our origin, right? And so if we want to be consistent with the last part of the problem, we need to keep the same origin. And so for the last part of the problem, we did the shank, we use the ankle as kind of like our point of origin, okay? And so we need to make sure we use the same point of origin here. And so if we use the ankle as the point of origin, then we need to add L1 cosine of theta 1. Okay. All right, and so since we need to use the ankle as our point of origin, we have to include kind of the x position of the knee itself. Okay, and so the one way that you can see this is that this extra term, this is the x position of the knee itself, and then from the knee we travel an r2 theta 2, r2 cosine theta 2, to get the x position of this one. Okay. Okay. Right, so visually it looks something like this. And so if we have kind of the ankle here, okay, so the ankle is our point of origin, okay. We have our knee, and so this length is L1, and then from this right here is M2, where M2, the center of mass for the thigh. Okay. And so to get the total, this is R1, and so to get the total kind of x position of the thigh, first we need to travel along the shank, okay? And so that's going to be L1 cosine theta, L1 cosine theta 1, okay? And then from the knee, then we travel R2, excuse me, that's R2. So we travel R2 cosine theta 2. Okay, so we kind of do like almost like a vector addition. And so we take a vector that goes from the ankle to the knee, and then to that we add a vector that goes from the knee to the thigh center of mass. Okay. Right. Any questions on this? Does that make sense why we have two of these terms here for the thigh? All right, and so I think that's the easy part of this. The hard part is going to be to actually take derivatives of this bad boy. So, all right, so let's take VTX, and so VTX here is going to be the derivative of the x position with respect to x. Okay, and so we have two terms here. So we have minus R2 omega 2 sine theta 2 minus R L1, sorry, minus L1 omega 1 sine theta 1. Okay. So that's what you get for after taking the derivative with respect to t once. Okay. And then we're going to take the derivative again. And then once again, we need to do product rule on both of these terms. Okay, so both of the terms are going to need product rule. And so overall for the acceleration, we're going to have four terms overall. Okay. All right, so let's get to it. And so we have minus R2 alpha 2 sine theta 2 minus R2 omega 2 squared cosine theta 2. Okay. So we have derivative of the first times the second minus the derivative of the second times the first, okay, or plus, excuse me. And then we have L1 minus L1 alpha 1 sine theta 1 minus L1 omega 1 squared cosine theta 1. Okay. Okay. So a bit more math here. You know, as you kind of get further away from your origin, the math kind of adds up to it. But just like before, just kind of make sure you're taking this kind of systematically, step by step, and you'll be able to get this. Okay. All right. So let's do the same thing for y. And so we have y ty. This is equal to r2 sine of theta 2, and then plus L1 sine of theta 1. Okay. And then let's take the derivative. So we have vty is equal to r2 omega 2 cosine theta 2 plus L1 omega 1 cosine theta 1. And we have aty. Here we have r2 alpha 2 cosine theta 2 minus r2 omega 2 squared sine theta 2 plus L1 alpha 1 cosine theta 1 minus L1 omega 1 squared sine of theta 1. Okay. All right. And so those are the accelerations in the x and y directions. And so just like the last time, you would take these expressions and plug them into the equation of motion that you see up here. Okay. All right. Any questions on this?
Yeah, Professor. So when we plug these into the expressions above, are we saying that omega and alpha are known?
Yes.
Okay.
Yes. That's a good question. So in these kind of kinematics expressions, all omegas and alphas are known. Because those are all part of the kinematics part. And so with a good motion capture system, you'll be able to capture the joint angles, of course, but you're going to also kind of measure those joint angles with respect to time. And so you can take derivatives of them to get omegas and alphas. Yeah.
Okay. Thank you.
Mm-hmm. Yeah, so even though these expressions look kind of nasty, in theory, you'll actually know all of these, at all values in time. And we didn't get to it today, but what we're going to start on Thursday with kind of one more example, and you'll see what it actually looks like, what that kind of data looks like, and how you can actually plug that into this expression. Because I know everything we did today was in terms of symbols, and so I think it'll help. I like to do the example with symbols first, just so that you can kind of see the whole process and kind of what it all looks like. And then I like to do an example with the numbers so that you can see how it hooks in. So we'll start with that on Thursday because we're kind of almost out of time here today. Okay. Any other questions on this? Okay. All right, and so like I mentioned, we are just about out of time, but I did want to make a couple notes, especially because I think now you're kind of in a good position to start the homework problem. Okay. All right, so the first thing I'm going to note is kind of if you remember when we started this example, we started at the foot and kind of worked our way upwards. Okay. And the reason for that was because we had measurements of the ground reaction forces at the foot. Okay. And so generally speaking, wherever you have your ground reaction forces or any kind of measurements of external forces, that's where you want to start your analysis. Okay. In the homework problem, I purposely gave you a case where you don't have the ground reaction forces. What you have instead is you have measurements of the mass and the moment of inertia of the upper body. Okay. And so this example could have easily been modified, and in fact, it is for the homework, where I don't give you these ground reaction forces. Okay, so FGX, FGY are not going to be known to you. Okay. And so in that situation, where you would actually start would be from the opposite side. Okay. And so even though it's not going to be ideal, it's not going to be as accurate as if you started from the bottom with ground reaction forces. If you don't have the ground reaction forces, you basically need to start somewhere where you can compute kind of like some kind of external force onto the system. Okay. My cat is here. She wants to say hi. Okay, let me just double check everything. Okay, and one thing I also want to say is that we're working with 2D examples here just because it's all that we can really compute. But of course, real life examples are 3D, and so you're almost always going to need a computer to do that. Okay, and so that's kind of another reason I'm showing you these equations, because it's useful to know how to set up these equations, and then once you kind of move to 3D, it's kind of the same process, except you kind of let the computer handle most of the calculations for you. Okay. Any final questions before we sign off for today? Okay, all right, and so that's it for today. And so I will see everyone in person on Thursday. And let me bring my cat here because she's being kind of annoying. So, my cat says hi, and I'll see you guys on Thursday. Hope you guys have a good day. Stay dry. All right. 442, yes. So we did talk about it last week in our faculty meeting. So I did request it. but there's also quite a few other classes that only I can teach that that the department might want to offer instead. And so, you know, it wasn't good news, I think, for 442, but you know, I did strongly request it. And so because the department there, the way it kind of works is that, you know, we have to offer certain courses, you know, with a certain amount of frequency. Otherwise, the courses kind of get retired. And so what's on the docket for next semester already is 417. So that one is likely going to be taught by me, although we do have another part-time faculty that can teach that one. There is a graduate course called 540, and so that one I think I'm most likely to teach because I don't know of anyone else that has taught it recently. And then there's also a course that's not on the schedule yet, which is called 454, which is called optimization. And so that one we haven't offered in 4 years, but if we don't offer it next semester, it's actually going to be retired. And so and I don't think anyone else can really teach that course except for me. And so I'm likely going to be teaching that one as well. I don't know if I'm doing advising next semester. And so if I'm not doing advising, then 442 would be my choice for the 4th class. But I don't know, because Dr. Weiss is going to come back next semester and Dr. Lieb is probably going to want to do advising again next semester. And so, you know, I think it's a decision that the department chair is going to make. But, you know, I've made it clear to him that I do want to teach 442. It's just, you know, it's just kind of where the department needs me there. That's where they're going to put me. Yeah. So I think last week I said it was probably 90%. I think now it's probably closer to like 50% chance. Yeah, but stay tuned. I'll keep you guys updated as soon as I find out anything. I'll let you know. Yeah. Yeah. Mm-hmm. I see any final questions? Okay, all right. I'll see you on Thursday.